Well, with all that preamble in the last lecture, what we are going to say next better be big. It better be good. And it is. These are called statically indeterminate. Axially loaded bars, but we're going to abbreviate that. Just say axial bars. Statically indeterminate. Now, we might want to define those as the contrary case for what we've been studying so far in statics. Your background has been such that you could find all reactions and all forces using only statics. So something like, a planar truss, something like this, and you've got a load here, you maybe have a pin here, and a roller here. So statically determinate, I'm abbreviating that. That means determinate. That means you can find all forces by statics alone. In other words, that is the only set of physical principles and governing equations that you need to find all the reactions. So if I ask you, find the horizontal reaction there, the horizontal reaction here, and the vertical reaction here, if the structure is statically determinate, all you need, I should say all we needed, is the sum of the resultant force, is the sum of the resultant moment, and those are all equal to 0. 6 equations, 3 of force, 3 of moment, and you could find that. Here's the problem. In real life, very few systems are like that. And they are statically indeterminate. And when something is indeterminate, they have a very distinct character. Let's set up a problem, and this is going to be one of the ones that we're going to be considering. And it's very enlightening. Let's say that we've got our bar, and in fact, we're going to make it of our 2 favorite materials, but instead of aluminum, let's say that we're going to use titanium and silly putty. And don't worry about what the areas are. Don't worry about what their lengths are for right now. But we know they have different properties. But now what I'm going to do is I'm going to fix both ends. Like so. Now, all of a sudden, and by the way, this becomes, as I load it with, let's say, 100 pounds. Now, all of a sudden, we have generated one of the simplest cases of statically indeterminate problems. Because we know that there is going to be a reaction at both ends. And they're both going to be going to the left. This is a very simple loading. So we're both going to get resistance. As I apply my loading at this location, it wants to compress the silly putty. It wants to stretch the titanium. And so I realize then that there's going to have to be reaction forces that are going to balance that applied load. We just don't know what they are. So there are reaction forces going to the left to balance that load of 100 to the right. Now, somebody might say, I know what the answer is. So the first student comes up, Marcia, and Marcia says, you say that's 100, I say that's 50, and that's 50. There, it's in equilibrium. But then another student comes up, Jan. Jan says, no, that's not it. I think that this is 100 and this is 0. But finally, a third student, Cindy. Cindy says, no, you're both wrong. That's 100. That's 0. All of those solutions satisfy statics. So some of the forces in the X are going to be equal to 0. And this is a characteristic of statically indeterminate problems. Basically, there are an infinite number of solutions to the equations of equilibrium. but they can't all be right. Only one solution exists for a unique value of forces that's going to satisfy equilibrium. So they cannot all be correct. Exclamation point. There is no way. And we haven't even heard from Greg, Peter, and Bobby yet and seen what they see. So what is going to be our approach to do this? Well, the first one is going to be more kind of qualitative. Notice what these two are saying. In fact, let's take the extreme case. Let's take Cindy's proposal right up here. Cindy says that basically all of the force is going into this bar. The silly putty is taking the entire load. The titanium doesn't take any load at all. And incidentally, in all of these cases, there's perfect bond between these two. Those two can't separate. Well, immediately we see that that cannot be. So on this case, it says the silly putty takes all of the load. The titanium takes no load. That means that the silly putty bar is compressing. And the amount that it's going to compress is PL over AE. So 100 times its length divided by its area divided by its modulus elasticity. On the other hand, this bar, the titanium, if there's no load, there's no axial stretch or compression. So you can see that's a problem, because what we're saying is that the silly putty compresses, it's getting smaller, which means that the titanium, if they're connected, needs to get bigger. But it can't get bigger because P is 0 in that one. We've assumed that there is no reaction force. So clearly that one is wrong. And what we have done, what we've used to kind of embed that inside is now going to be formalized as we work our way through this particular analysis. So we are going to close out today by talking about the 3 basic tools. Now, some people may call this 3 basic criteria. They could call it the 3 basic tools, the 3 basic principles, but we'll go ahead and use tools because what we need to do is use all of those to solve our problem. So 3 basic tools of solid mechanics. And I'm going to box that up. 3 basic tools of solid mechanics. And if you'd like to, you can think of it as some set of physical laws that has to be enforced. So the first one is going to be statics. Now you might say, well, we've already done that, and that's correct. But it means that the deformed solid must be in equilibrium. And we've been using that so much that it's almost second nature. So that's really kind of a given. You have spent an entire semester practicing these. And so practicing these principles and applying them to a wide array of problems. So this one, I would say you've got kind of cold. The second we will use, the phrasing that we'll use, will be stress-strain laws. And what we're going to say in that is that the deformed solid must obey, maybe that's the wrong word since it's an inanimate object, I'll put quotes around it, must obey known material laws. So for example, sigma is equal to E times epsilon. Now for the axial bar, it's going to be pretty simple, and it's kind of cool how this works out. So the axial bar, remember the stress-strain law, let's just write what we did upstairs. So that's going to be sigma is equal to E times epsilon. Well, if we've got an axial bar that has uniform properties, which most of us are going to have, then the stress is P over A, force divided by the area. Then we have E here, and the strain, the normal strain, is change in length over length. Well, our change in length is delta, and our original length is L. So now what we're going to do is we're just going to move L up here and bring delta down here. Oh, pardon me, not delta, we're going to bring E down here. So what does that give us? Delta is PL over AE. So the known material law manifests itself as our expression for the axial displacement. So this will always be the case in all the problems that we're going to originally consider. So the stress-strain law actually looks like our formula for the axial displacement. So that's kind of cool. All right, so it has to obey known material laws. That may seem kind of obvious, but the third one, we're going to use the word that is probably going to be new to most of you, and that is compatibility. And that sort of riffs off the cases that we were just talking about earlier, where we have the silly putty and the titanium. If the silly putty takes all of the load, it has to compress, but the titanium, it has no load, it's just sitting there undeformed. Well, that's a geometrically unacceptable deformed state. So what we will say is the deformed solid must be geometrically admissible. Geometrically admissible. What does that mean? There are going to be no gaps. I'll put this parenthetically. There are no gaps. We would have had a gap if the silly putty had shrunk and the titanium had just sat there. There would have been a gap between the point of connection. That can't be. So there are going to be no gaps or overlaps. In our deformed solid. So those are the big three. And we want to write those down on our sticky note so that we remember them. And when we come back for our next lecture, then we'll apply them in the types of problems that we care about. And we're perfect timing at 12 and a half right now.